into the reach of a reasonable carbon price. Those are the policies we need. Is it affordable? You can do a very rough calculation. If we paid an average of $100 per ton of carbon, which is near the upper end of that range in the previous graph, to avoid half of current world CO2 emissions, arithmetic is very simple. That would cost $500 billion a year, which is under 1% of current global world product, and much of that would be a transfer, not a loss. If we actually use that McKinsey Corporation cost curve that I showed you in the previous two slides for what we'd need to be doing in 2030 to be on a stabilization trajectory that gives you a better than even chance of staying below 2 degrees C, the net cost, because you make money on some of it and only pay money on some of it, the net cost is only about $100 billion a year. Current economic models, a more sophisticated approach to this, say that mitigation to stabilize at 450 parts per million of CO2 equivalent would be something like a 2 to 3% loss in gross world product in 2030 and 2100, with a range among different studies going from 1% to 5%. It's important to know that the world now spends 2.5% of its economic product on defense. The United States spends 5% on defense, and we already spend 2% on environmental protection, so these numbers aren't crazy. Now finally to the education questions. How can the answers about science better inform the answers that publics and policymakers embrace about what to do and when to do it? Clearly, this can only happen through more effective education and more effective communication. What are the ingredients of that? Communication, some ingredients. Start with the basics, be clear about terminology, explain how we know what we know, link it to what can be observed, and link it to regions and communities, the places where people live. In terms of education, what do we need to do? We need to focus in our education, first of all, on how science works and the sources of authority and credibility in scientific findings. And the longer-term project, of course, is we need to lift the level of science, technology, engineering, and math education overall to get the better educated, more science-savvy citizenry that we're really going to need in a democracy to deal with this problem and many others where science and technology play major roles. Let me just elaborate on this for a moment. Starting with the basics. What are the basics of what might be called the energy and climate challenge? Here are the basics. Without energy, there is no economy. Without climate, there is no environment. And without economy and environment, there's no material well-being, no civil society, no personal or national security. And the problem is that the world is getting most of the energy that its economies need in ways that are imperiling the climate that its environment needs. That's what I mean by starting with the basics. Terminology. Global warming is a misnomer. It's gotten us into trouble. It's misleading. It implies something that is uniform across the planet, that's mainly about temperature, that's gradual, warming is gradual, and that's quite possibly benign. Again, how could a little warming be bad for you? What's actually happening, the reality is highly non-uniform across the planet, not just about temperature. It's rapid compared to the past capacities of both ecosystems and societies to adjust, and it's going to be harmful for most places and most times. Even if some places for some period get some benefits, it's going to be harmful for most places and most times. And therefore, if we were being more accurate in our terminology, we wouldn't call it global warming, we'd call it global climate disruption. Now that's a mouthful, but it has the benefit of being accurate. Continuing with the terminology, we've got to be clear about weather and climate and disruption. Climate means the patterns of weather, the averages, the extremes, the timing, the spatial distribution of hot and cold, of cloudy and clear, of humid and dry, of how much it rains, of how much it snows and when, of how hard the wind blows all the way up to hurricanes and typhoons. And climate change means disruption of the patterns. The global average temperature is just an index of the state of the global climate as expressed in those patterns. It's like your body temperature. If somebody said to you, you don't care if your body temperature goes up 2 degrees C, that's just a little bit, 3.6 degrees Fahrenheit, what's that? You know if your body temperature goes up 3.6 degrees Fahrenheit, it's telling you something about the state of the system. It's just an index of the state of the system. And a little change in the index means a big change in the state of the system, and that's as true in climate as it is in your body temperature. Link it to observables. This is the storm in October 2010, the non-coastal storm, which was the strongest U.S. non-coastal storm on record, spawned 67 tornadoes over a 4-day period. People are starting to get it because they can see on their television, if not in their backyard, what is happening. Heat waves, Russia in the summer of 2010, the hottest, longest heat wave in recorded Russian history. This is Moscow, you can hardly tell, Moscow in the summer of 2010, from smog, heat-related, and peat fires. Flooding in Australia, 2010 and 2011, the wettest flooding, the costliest natural disaster in Australian history. Coral bleaching. Anybody who puts their head underwater can see that. 2010 brought the worst coral bleaching since '98, and '98 was the worst that had ever been observed up until that time. Link it to the local. These are wildfire predictions from the National Academy of Sciences showing for the western United States the expected percentage increases in the median annual area burned for a 1 degree C increase in global average temperature. Look at those percentages, 200%, 300%, 470%. This brings it home. We are already suffering from wildfires. This has long, I think, been the sleeper in the climate change business for parts of the world that are vulnerable to wildfires. Linked to the local, sea level rise. This is a picture produced by a former graduate student of mine, Jeff Balicki, showing for the Cape Cod and Boston area what the effects are of the various increases in sea level that are possible over the next few hundred years. Rather dramatic. One can make these kinds of plots for any coastal region, and it tends to get the attention of the people who live there. How science works, and I'm getting close to the conclusion. I know the Chancellor's getting on the edge of his chair here. How science works. First of all, people need to understand that uncertainties are two-sided in science. There's a tendency in the public to believe that uncertain means when we learn more, it'll turn out not to be as bad as we feared. And it could turn out that way. It could be that the climate changes that occur under continuation of business as usual will be less disruptive, and the adverse impacts on well-being less severe than what is currently projected by the scientific mainstream, the numbers that I've been providing, the graphics I've been showing. Those come, again, from the National Academy and the IPCC. But what people need to understand, again, is that uncertainties are two-sided. It could also turn out that the climate changes under business as usual will be more disruptive, and the damages to human well-being more severe than the mainstream consensus suggested. In fact, there are recent results to say that this uncertainty may in fact be asymmetric, skewed, alas, in the pessimistic direction. Second thing about how science works is burden of proof. The skeptics rather routinely brandish some single contrary piece of evidence or analysis, very often a newly reported one that hasn't yet been subjected to the scrutiny of the scientific community, and declare that this one new result invalidates the mainstream view about climate change. Now, that isn't how science works. Contrary results, as all the scientists in the room know, appear constantly in every scientific field. But when a strong preponderance of evidence points the other way, as in the case of climate change science, isolated apparent contradictions are looked at, they're given scrutiny, but they're not initially given very much weight. They're not initially assumed to be correct, and that's because it is far more likely that the supposed contradiction will turn out to be explainable as a mistake or as otherwise consistent with the preponderance of evidence than it will turn out that the preponderance of evidence is wrong. Matter of burden of proof. Third point on how science works, prudence. All science is contingent. We always have to admit that. It is always possible that persuasive new evidence and analysis will come to light that changes the mainstream view. From time to time, this happens. But the greater the consistency and the coherence of the existing body of evidence and analysis, the lower is the likelihood that the principal conclusions derived from that body of evidence and analysis will be overturned. And the consistency and the coherence of the evidence and analysis supporting the mainstream view of climate change and the risks of climate change, bodied in the reports of the NAS and the IPCC, but not confined to that, are simply enormous. And what that means is that policymakers on whose decisions the preservation and expansion of the public's well-being depends are gambling against very long odds if they bet that the mainstream position is wrong. That is simply not prudent. Now, I'll simply conclude by saying that the much longer-term project of raising the overall level of STEM literacy across our society would need to be the topic of another lecture. In fact, it was the topic of Carl Wyman's previous Langenberg lecture here. I'm sure he could give several more, but I'm going to leave that for future lectures and as an exercise for the audience. Thank you very much.
Thank you so much.